All right, 6.7 determinants. So it's 6.7 determinants. We're going to define and calculate determinants and then use determinants to find areas of regions. So we're really not going to find determinants to find areas of regions. What we're going to do is to find, uh, to solve systems. So we're going to talk about using determinant to solve system, which in turn will be about finding areas of regions because linear systems come into play when you're doing things like that. All right. By a show of hands, how many of you plan on going into some field of engineering? Maybe, a couple, few. Okay. So for the ones who plan on going into some type of mathematical or science-based engineering, you will dive way deeper into matrices than you ever wanted to. Okay. The rest of us, we're going to keep it baseline. All right. But the other people, yay, go make our worlds easier. And we appreciate you. But essentially, what we need to know is what a determinant is. Okay. A determinant is a number associated with any squared matrix. So in the 6.6 notes, I talked about a squared matrix is a matrix that has the same number of rows and the same number of columns. So 2 by 2, 3 by 3, 4 by 4, dot, 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 right? Those are squared matrices, okay? If A is a squared matrix, then there has a possible determinant, okay? When you see absolute value of a matrix, it means determinant, okay? The absolute value of a matrix doesn't mean you're going to go in there and take all the elements and turn them to positive, okay? Absolute value of a matrix means that you're going to find its determinant. So determinants are used to characterize whether it's invertible or not, meaning that there's an inverse to this determinant, which in turn I can use to help solve all these kind of problems, right? So absolute value of a matrix is an absolute value. It is determinant of that matrix. Got it? So if you see this little symbol here, that's what that means. All right. If it equals 1, then the matrix does not have a magnifying property. Again, these words are irrelevant for us non-engineering people right now. Okay. If it's less than 1, the matrix has a magnifying property. If it's greater than 1, the matrix has a shrinking property. Okay. And then if it's equal to 0, it can shrink any object to a dot, or the matrix is not invertible also. Okay. The piece that we care about for our class is this. All we care about this. The matrix is not invertible. The rest of those are for engineering people. Does that make sense? All right. Now, how do you find the determinant starting off as a baseline? This is the formula that we use to find the determinant of a 2 by 2 matrix. Okay. Raise your hand if you know how to multiply. Raise your hand if you know how to subtract. Guess what? You can find the determinant. Okay. Because those are the two skills required to find the determinant, is to be able to multiply and to subtract. If you could do that, then you're golden. Okay. So let's practice. Are we ready to practice finding the determinant? We're going to find the determinant, and then we're going to decide, based on the value of the determinant, if the inverse exists or not. Okay. In your 6.6, you talked about inverses, and the way that you verified whether inverses exist or not, or two things were inverses of each other, is where you had to multiply them. Multiplication came from the previous units. If you aren't watching the matrices unit in order, then it will be confusing. It's not a unit that you can jump around in. It actually is a unit that builds on top of each other. Okay. So you need 6.2 and 6.3, and you're able to do 6.4 to do 6.5 to lead to 6.6. Okay. It is not a unit that you can jump around and be okay with. All right. Okay. Let's practice our multiplying and subtracting skills. Why is the answer there? You saw nothing. All right. So up first here, we have matrix A, the first matrix A, and we want to find its determinant. And then based on the determinant, decide if it has an inverse or not. So we're looking for the determinant of A. When I'm looking for the determinant of A, that means I am simply doing what? I got to cross multiply and subtract. So we have 4 times 4, which is minus 5 times negative 6, which is negative 30. A negative times a negative makes a positive. So the determinant is 46 because the determinant is not equal to 0, doesn't equal 0. There means that the inverse exists. Bam. How we feel? Hit it. The determinant, well, in terms of our class, it's just letting us know whether it has an inverse or not. Outside of our class, it's its magnifying and shrinking property. But that's irrelevant for us. Okay. But ours is just, it's a number that tells us whether there's an inverse that exists. Bless you, bless you. All right. So let's try another one. So over here, this A, so I'm looking for the determinant of matrix A. Again, you cross multiply. Negative 4 times 5 is negative 20 minus other cross. Negative 20. A negative times a negative makes A. So I now have negative 20 plus 20, which equals 0. Because it's 0, that means that does not exist. Does not exist. D and E. Okay. Ta-da. How do you feel about 2 by 2 determinants? Okay. If you can do a 2 by 2, you can do a 3 by 3. It just requires a little bit more work. Just a little bit. Yeah. Okay. Just a step. Well, like just a little intuitive. Right. All right. So again, we got 46, which told us that it is an inverse exists. We got 0, which tells us that it does not. Cool. All right. Now let's talk about minors and cofactors. Okay. Minors and cofactors are what are needed for us to find determinants of matrices that are greater than 2 by 2. Okay. So when you have a minor and cofactor, your cofactors are the elements and the rows and columns that you eliminate. Okay. Your minor is what's created from that. Okay. So if we look right here at matrix A, a matrix A is a 4 by 4, right? 4 rows and 4 columns. Agreed? So matrix A is a 4 by 4. Well, if I was wanting to find the determinant of a 4 by 4, I need to make it all the way down to a 2 by 2. In order to make it start breaking it down to a 2 by 2, I have to use cofactors in order to make a minor matrix. Okay. Your cofactors are the rows and columns that you eliminate. Let's see. Let's see. Thank you. Okay. So here, for example, this says A24. Okay. A sub 24. What that means is it wants you to, let's see. It wants you to eliminate row 2, column 4. So row 2, column 4. Those are the cofactors that I'm getting rid of. Does that make sense? So 2, 4, it's always RC cola. Okay, RC cola. Rows, then column. Row 2, column 4. And when I eliminate that, what I'm left with is the minor for this matrix. And my minor would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Yes? So the main part here is just terminology. All right? That's what we're focused on is the terminology. The cofactors are what the rows and columns you're eliminating. The minor is what's left over after the elimination. Okay? So we have our if I can write. We have our cofactors. And what's left over is our minor matrix. Cool? All right, so we're going to practice finding this. What we're not going to worry about is A. A is your, I don't know. Yeah, erase. Ignore her. Focus on this. So we're going to find the minor matrix um, of M22. So M22 means that I am doing what? M sub 2, row 2. So when I cross out row 2 and column 2. And when I do that, what am I left with? Could you find the determinant of this now? And what would be its determinant? There you go. Okay. Yes. All right. What about M21? Would the process be any different? No, it would not. So again, we had M22. We cross out the row 2, column 2, and we were left with this new matrix that's a 2 by 2, which I can easily find its determinant. And the determinant was -2. Okay. Same premise here. We have matrix, we have M21, uh, minor sub 2, 1. Let me say it correctly, I guess. But M21, you know what I meant. So we're going to eliminate row 2, column 1. And from there, my minor matrix that is created is 2, -3, -1, and -2. Now that I have this minor matrix, can I use the 2 by 2 rule to find its determinant? Yes. And the determinant would be, say it again. You were good. You did the last part wrong. -4 -3. There we go. All right. Yes. All right. Why are minor and cofactors important? Because when you're trying to find the actual determinant of a 3 by 3, you have to use the minor of minor 1, 1, minor 1, 2, and minor 1, 3. I said it wrong. I said it right. Yeah. Row 1, column 2. Row 1. Yeah. Okay. So we're gonna watch a quick little video um of how that looks and where it goes. We're just watching the video for the rule, and then we're gonna apply the rule. Does that make sense? So we're not gonna watch all of the video. All right. So we're gonna watch Patrick. Ignore that part. Can't really do that about it.
They you either write det of a or they put in looks like absolute value, and it says to compute the determinant of a 3 by 3 matrix. Basically, what you do is if you look at stuff along the top. Okay, so I'm going to look at my A11. Basically, the formula is you take that term A11, and I imagine kind of canceling out that row, or excuse me, that column and that row. I think, what am I left with? I'm left with a smaller matrix, A22, A23, A32, A33. Okay, so I'm going to take this coefficient A11 times this smaller determinant, and really calculate a smaller determinant. Multiply the diagonals and subtract the product of the other kind of diagonal. So I assume if you're looking at a 3 by 3 matrix, you know how to do a 2 by 2, but we'll talk about this in a second as well, just in case. So now we do the kind of the same thing. We look at the same row, but we move over. Okay, we look at that guy. It turns out that there ends up you have to change the sign, so it's going to be A sub 1, 2. And again, I think if I were to cover up that column and that row, the stuff that I would be left with would be the A21, A23, the A sub 31, and the A sub 33. Okay, looks like I'm running out of room here. And then we go to the last one as well. So Okay, so the same thing, I look at the A sub 1, 3. I imagine covering up that row and that column, and I'm left with the smaller determinants. A2, 1, A2, 2, A1, and A. Kind of basic formula for computing a 3 by 3 determinant. So pretty tedious.
Okay.
Oh, but you take the top row.
We have to find the determinant. So this is the formula. Yeah. So exactly. So you have your cofactors, right? So your cofactors are based off of your leading elements in row one. So whatever row and column those elements are in, those are your cofactors, which means you're eliminating them. After you eliminate your cofactors, you're making your minor. Your minor is made up of what's left. And then once you set it up, now it just comes down to finding the determinant and then multiplying by your leading row. And then you multiply it. Yep. All right. Are you ready to try it? Yes. Okay. Let's dive on in. We'll start with easy numbers. How about that? I'll give you a moment to write her down. Okay. So ready? All right. So typically when I was doing this as a student, I had 3 different color pens and 3 different color highlighters. But as he modeled, you can always just cover up with paper, right? So there's like post-it notes or something. If you like the cover up method, then you can use the cover up method. I'm gonna model it using my highlighter and color method. But again, it's totally up to you which one works best for you. Okay. So I also start off by reminding myself it's gonna be plus, minus, plus. Okay, so we're finding the determinant of A, which equals. So I'm starting with my first element and row one, column one. So my first element and row one, column one is 2. So what that means is that to find here, that's a cofact, those are cofactors, and that's cofactors. Okay, so therefore my minor would be 3, 1, 1, and 4. Is what? Yes. Okay. And then the next one, but remember, so the first is positive, the next is going to be negative. My second element, which is 3, that second element is in row 1, column 2. So those are its cofactors. And what I'm left with is going to be 0, 1, -1, and 4. Plus, my last element is -4. It's in row 1, column 3. And I'm left with 0, 3, -1, and 1. So that's the setup. Okay. After we've done that, the second step is going to be is to find your determinant of each one. Okay. So we're cross multiplying and subtracting, cross multiplying and subtracting, cross multiplying and subtracting. So we have 2 and 3 times 4 is 12 minus 1 times 1 is 1 minus 3. 0 times 4 is 0 minus -1 times 1 is -1 minus 4. 0 times 1 is 0 minus -1 times 3, which is -3. So we have 2 times 11 minus 3 times 1, because a negative times a negative is a positive, minus 4. And again, a negative times a negative is a positive. So we get 22 minus 3 minus 12, which equals double check my math.
So we don't times them with their derivative until
The determinants at the end.
the
Yep. Parentheses first, remember PEMDAS? All right, how you feel? Doable? Guess whose turn it is? Oh my gosh, you're so smart. Here's yours. Feel free to use a calculator. Numbers are a little larger. Just a little bit. All right, friends, let's see how you did. So how was the setup? Was it terrible? Okay. So for your setup, your first element was 2. After eliminating its cofactors, you should have had -2, 5, 19, and 10. Okay, remember plus, minus, plus. So now we have minus 24. After eliminating its cofactors, we're left with 1, 5, -7, and 10. And then our last element was plus, -1. After eliminating its cofactors, you're left with 1, -2, -7, and 19. Yes? All right. For the sake of multiplying, I'm just going to use the calculator. If that's okay with y'all. So I don't embarrass myself with the big numbers. All right, so I'm going to start the first one. So for the first one, I have 2 times -2 times 10, which is -20, minus 19 times 5, which is 95, close parentheses, minus 24 times 1 times 10 is 10, minus 5 times -7, which is -35, minus 1 times 1 times 19 is 19, minus -7 times -2, which is 14. 14. And I hit enter, and I get -1,315. How we do? Doable? The determinant of A equals 1,000. -1,315. All right, good. All right, let's talk about past the 3x3. When you get past the 3x3, it becomes very, very, very tedious to solve. The reason being is that if I have a 4x4, I have to find its minor matrix to make it a 3x3, then take the 3x3 and turn that into a 2x2, right? So if you think about it, I would have the 4x4s, which would break down to 4 3x3s, right? And those 4 3x3s then would break down to 3 2x2s. Does anyone want to do that? No. So after we get past the 3x3, I'm going to strongly encourage you to use the calculator. Okay. The steps in the calculator are fairly easy. You're going to input the matrix. You're going to click on the matrix, arrow over to math, press determinant, and then go back to your matrix and put the matrix and find the determinant. Okay. So we're going to go through these 4 steps, and hopefully you're like, oh, I could do that. All right. Here's Big Bertha here. And nobody wants to do that by hand, right? Now, if you do, I won't stop you. If you just want to challenge yourself because you got plenty of paper to write, go for it. All right. So I'm going to clear my calculator. Second plus 712. Sylvia's been cleared. I'm going to go to second, x to negative 1. I'm going to input my matrix. I go over to edit, and I have a 4 by 4. I'm going to input as I type. I'm going to press enter, and that allows me to be able to put the next element in. If the first time you try to do this is on a test, not a good idea. So it's a really good idea to make sure that you're practicing the skills before the test. All right, so I have all of my elements in. After I'm done, you have to close out of the editing window. To close out of the editing window, we hit second mode. So our editing window is gone. Now we're going to go to second, x to the negative 1, arrow over to math, and you see where it says DET. That stands for determinant. Press 1. I'm going to go back to that same window, and you see my 4 by 4 was built, right? I'm going to click on it, hit enter, and it says, cool, here's your determinant. So we know that the determinant of A equals negative 11,280. There. Questions about doing it in the calculator? You have to go all the way down to a 2 by 2. Yeah. Like you want to be lazy? You didn't want to cross multiply and subtract? Because that's not a huge brain. That's a lazy brain. Oh, well, what if I just want a 2 by 2 by it? Yes, you can. Okay. All right. So, question came up. Let's double check that my numbers are correct. No, it should be the same. I have 2, negative 4, negative 5, 5. I have 2, negative 4, 7, 2. I have negative 9, 23, 12, and 7. I have negative 8. See, look. I have 2, 3, 3, 3. I asked you guys to double check me. I can't see these tiny numbers over here. I told y'all, look, I said, hey guys. What? What kind of nonsense is that?
That's star test logic.
Oh my gosh.
Closest to what you got.
How embarrassing. Y'all just let me. I literally asked you guys, did I put that in right? Every last one of y'all. You did lie to me. Y'all told me yes. Y'all lied to me. I had 2 numbers wrong. But do you see how having those 2 numbers wrong throws off your problem? Make sure you just make sure you type it in there correctly. Or don't ask people to help you, apparently, because they're gonna still you're gonna be wrong. So you didn't watch my video? Take the notes? No, you did not.
He showed up 30 minutes early and he's like, nah, man, it didn't work. I tried to join. I tried. He took a nap. Jorge was tired. Like, just say you were tired.
Excuses. All right. Here we go. The last thing that I'll teach you in college algebra. Oh my gosh. We've come to the end of the road. All right, our very last thing is called Kramer's rule. So Kramer is some guy who apparently had a whole lot of free time. And he realized that, you know what? You can use determinants to solve systems of equations. Yeah. Imagine what type of brain freedom you had to have in order to do that. Um, I'm pretty sure this was a time before technology. Uh, it had to be a time before technology. But he realized that you can use it to solve systems. And so it's actually a fairly simple way of doing it. Um, but you have your system. We all are familiar with this from our previous unit, right? So you have your system. You're going to define your x value. To find your x value, your constants are your first column elements, and then your coefficients of your y are going to be your second elements. Okay, your constant to find x, m and n, which are your constants, and then you're going to take whatever has the y, your coefficients. Yeah, I mean, if you're good at multiplying and subtracting. Okay, and then on the y, it's the opposite. So since I'm looking for y, I'm going to take the coefficients of my x and put them in the first column. Then I'm going to take my constants and put them in the place of my y. So what you're looking for has the constants. Does that make sense? So here I'm looking for x's. So instead of writing the coefficients of my x's, I'm writing my constants. I mean, at this point, you have multiple ways of solving a system. This is just, yeah, if you want to do it Kramer's way, yes. Okay. Now, your denominator is the same. The denominator is just made up of your coefficients. A, B, C, C, D. Whatever your coefficients are, that's what your denominator. They're exactly the same. Exactly. No. So when you're solving for x, notice that your constants are first. When you're solving for y, your constants are second.
Or he's like, do I really need to write this?
No, I wrote it down, but I'm asking like functionally, like you never did this. This doesn't like a feeling.
It looks a feeling deep.
If you like doing determinants, it is.
Well, yeah.
I don't know. Okay. All right. And then your denominator are all your coefficients. All right. Let's just see it. It's our last lesson together. So let's dive on in. So here's our example. Now, do you have skills to solve this in other ways? Yes, you do. Okay. Do not throw away those skills. This is just hey, here I am. There's another way of doing this. Okay. So do not disregard what you already know. Okay. So we're going to start off with our x. So x equals the absolute value of your constants first. Not absolute value. The matrix is made up of your constants and then your coefficients of your y's, which are 5 and -9. Your denominator is all of your coefficients. So we have 3, 7, 5, and -9. Yes, that's your x. Your y is the opposite. A what? What did I write? Oh, I wrote 78. Thank you. Thank you. Okay. And then we have our 118, -76. And then we have 3, 7, 5, and -9. Bam, all set up. And then at this point, you just got to find the determinant. And how do we find our determinant? Determinant, we cross multiply and subtract. Okay, you can do it by hand or, yes, your bottom you have to do once because it's going to be the same. So now we're going to find the determinant, and I'm just going to use the calculator. Turn Sylvie on. Turn Sylvie on. She's tired like me.
Only one semester.
All right. I cannot see it all the way over there, Sylvie. Come back. Come a little closer. I'm blind. Why can't you? There you go. All right. So I'm going to do the first one. So I don't know what 118 is. Why does it want me to do that? I just want to put it here. You know what? You guys can see it, right? You have it written on your paper. All right. So I'm going to do it here. So we have 118 times -9. Please just go. -9 minus -76 times 5. So that's my numerator, which is -682. My denominator, it's going to be, and notice, I'm not even trying to math for real. I'm putting it in and letting the calculator do it. Minus 7 times 5. And I get -62. And then I'm going to divide those. So we get 2 divided by, and I get 11. So x is 11. And I'm going to do the same thing for y, but I only have to do the numerator because I already know the denominator is -62. Yeah, so we have 3 times -76 minus 7 times 118. Hit enter, and this divided by -62, and we get 17. So y equals 17. So the solution to this system would be 11, 17. Could you do elimination? Yes, you could. You could have multiplied the top by 9, the bottom by 5, canceled out your y's, combined your x's, wham, bam, all those things. So it's just another method. Make sense? An ordered pair. Remember, the solution to a system is a ordered pair. That's it.